Hello, my name is Hassan Gharedaghi, and this is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. This talk is titled Easy CDM and is based on a work supervised by Dr. Jamal Amanirad at Shahid Beheshti University, Iran. This talk is about fitting a model of continuous decision tasks to data. First, I will briefly talk about the evidence accumulation with an example of the diffusion decision model. Then, continuous decision tasks with the circular diffusion model are discussed. And then I will present the fitting method and show its performance. Evidence accumulation models encompass a class of models with a common neurophysiologically supported assumption that the information over time is integrated to be represented by a state value that evolves according to the new information gathered or processed in time, until it reaches a threshold for triggering the decision. One such model is the diffusion decision model, abbreviated as DDM. In this model, the state point represents the relative accumulated evidence of two options. The state value changes continuously in time and evidence space according to the Wiener diffusion process, which is a limit of random walk, taking independent and identically distributed tiny steps in tiny time intervals. Each option has its own threshold, and when the process reaches one of them, the action for choosing the relevant option is triggered. So the model is based on some intuitively natural assumptions, which of course justifies its extensive applications. The DDM is for modeling the two alternative decision tasks. But it seems that the human is mostly confronted with tasks requiring choosing between a continuum of options. For example, decisions like planning multiple muscles movement to reach something with a hand, or deciding where in the space to scout to, or more internal decisions like making judgments on sensory information to construct perception about color or direction. One example of continuous decision tasks is presented here, where the participant should recall the color of the probe discovered from memory and choose the color from this color wheel. The circular diffusion model, or CDM, is an evidence accumulation model that models the tasks in which the options are arranged around a circle. For example, the direction, orientation, and color can be of a circular type. In the circular diffusion model, the state of accumulated evidence is represented as a point in a two-dimensional plane. The state point dynamic in time is a Wiener diffusion process with a drift vector, which indicates the systematic movement tendency of the process. On average, the state point tends to change in the direction of the drift vector direction and at the rate of drift vector length. So the drift vector direction indicates the intended option to choose, and the drift vector length is an indication of evidence accumulation speed. The decision is made when the state point reaches a threshold distance from the origin. The heading point determines the choice, and the time to hit plus the non-decision time determines the response time. The parameters of the model are the drift vector direction, drift vector length, boundary distance, and the non-decision time. The popular and extensive use of the CDM requires developing easy-to-use fitting routines to estimate the parameters' values from experimental data. Generally, the maximum likelihood estimation method, or MLE, is a suitable choice for estimating the parameters of stochastic models. The MLE consists of finding the parameter values that maximize the likelihood of observing the data. For example, one desirable aspect of the MLE is its asymptotic efficiency, meaning that when there are enough data, the estimates are the closest possible to the data-generating values of parameters. Using the maximum likelihood estimation for the CDM is somewhat problematic. As we will see, the likelihood function is an infinite series and there is a challenge with its precise calculation. Also, reliable optimization phase is required here. So the need for some mathematical and programming skills hindered the popular use of the CDM. The method of moment is another option for estimation. In the method of moments, the parameters are estimated in a way that the first moments of the data and predicted distribution become equal, and the estimates are calculated by solving the system of equations, which could be easier than implementing this MLE. Here I represent a simple procedure for fitting the circular diffusion model to data and show the results of its performance. The MLE will be used whenever there are simple, straightforward formulas for its estimations, and the method of moments is used when there is no such simplicity. This is the likelihood function for the circular diffusion model. V is drift length, A is threshold, theta V is drift angle, T0 is non-decision time. I and J are Bessel functions, and this J is Bessel 0. T is response time, and theta is the choice angle. The first term here is only dependent on response time and integrates into 1, and the second term is only dependent on the choice angle. So the first term is the marginal response time distribution, and the second term is the marginal choice angle distribution, and the two are independent of each other. So the coincide of the response time and choice angle in trials is not important, as we can gather all data points together. Let's first look at the response time data. The distribution is a famous one called von Mises, having two parameters of mu as mean and kappa as the concentration of the distribution. Comparing the two formulas, we can see that mu equals AV and kappa equals theta V. The von Mises model is a well-behaved model, which its maximum likelihood estimates of parameters satisfy these equations here. The right-hand side is called the angular mean and variance of the data, and the left-hand side is the angular mean and variance of the model. This way, we get two equations. To build a solvable system of equations for the four parameters, we need other two equations, which we will build from choice angle data by using the method of moments. The choice angle distribution is the first passage time of a Bessel process with drift, which is the length of a two-dimensional Wiener diffusion process. To use the method of moments, we need the first two moments of the model, which can be calculated from the moment generating function of the distribution available for this model. It's a routine practice. Looking at the Taylor series of the function, it can be seen that moments could be calculated this way. It's more popular to work with variance instead of the second moment, so we could calculate the variance as here. Now we have all our four equations. First, angular mean and variance of the choice angle data and mean and variance of the response time data should be calculated and placed in the system of equations here. Now let's try to solve the system. The first equation directly gives the drift angle. We could also solve the second equation for AV, and then rewrite the fourth equation with respect to V and solve it for V. Then calculate A, as we have both AV and V, and use the third equation to calculate the non-decision time. So to estimate the parameters in EasyCDM, we only have to calculate the statistics here and do the calculations here. Now we illustrate the performance of this estimation method. We simulated data from specific parameter values and compared the estimated parameter values from the data with the actual data generating parameter values. The MLE is also implemented as a reference estimator to compare the performance with that. The data sets are of size 100 or 1000. This plot illustrates the performance of recovering the drift length. Each point is for a data set that shows the estimated value against the actual parameter value. The first row is for data set size of 100 and the second row is for 1000. The left column is for the MLE and the right is for the EasyCDM. There is no evident bias and there is a slight increase in the variability of the EasyCDM estimates compared to the MLE. This plot is for the threshold. Also, no evident bias here, and there is a desirable variability level. There is no need to use variable values for drift angle and non-decision time, since looking at the procedure for the EasyCDM estimation and the MLE, it can be checked that the change in these parameters will only change the relevant estimated parameter to the amount of the change in the data generating parameter value. So we use the constant value of 0 as data generating drift angle. The estimates of the EasyCDM are the same points as the MLE, because the estimates was based only on choice angle data which maximum likelihood was used. The constant value of 0 is used as the data generating non-decision time. There is no evident bias, but variability is evidently higher for the EasyCDM. One problem with experimental data is that they always contain some contaminants, that their presence is not considered in the model. To investigate the performance of the EasyCDM in presence of contaminant data, we added a random uniformly sampled number from 0 to 2 seconds to 5% of response time data points. The recovery results are compared to the maximum likelihood estimates of uncontaminated data. Red dots are for the EasyCDM, black is for the MLE, columns are for drift length, drift angle, threshold, and non-decision time. This bad performance could be traced to the nature of the statistics used. The mean and variance are very sensitive to contaminants, but there are more robust statistics for central tendency and dispersion. Recalling that using the method of moment turned out okay, and the performance of the method of moment actually depends on the similarity of the distribution to normal. So normality assumption didn't turn out so bad. Therefore, here we also suppose that the distribution is normal. In the normal distribution, the median of the data could be also an estimate for the mean of the distribution, and the interquartile range will be a constant factor of the standard deviation of the distribution. So we can replace mean and variance with these more robust statistics and do the same calculations in the EasyCDM. Here is the parameter recovery performance of the new robust EasyCDM method. In the presence of contaminants, it performs well. Note that the MLE is on the uncontaminated data. The MLE performance would be terrible on the contaminated data. As a final point, taking into account the nature of the statistics used, we can expect that the robust EasyCDM is still robust against other types of contaminations and also against outlier data points. The tutorial for implementing both the simple and robust version of the EasyCDM is available at the web address here. And thank you for your time and attention.